The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so by this time, most of you should have had your meetings with your masters. How many of you had meetings with your masters? Okay, who didn't yet? Today and Friday. Okay, who haven't scheduled a meeting? So are you talking to them, and do you know? Okay, make sure you get masters meeting scheduled, okay? Because this is a very important part. We are getting feedback from the masters. I think they are giving you guys a lot of good advice. And so make sure you schedule, you go, you meet, get that resource, use that resource. It's very hard to arrange that kind of a senior person spending a lot of time with only 2 of you at a given time. And that's a really good ratio to have. So take advantage of that. Okay, so also I think at this point most of the beta issues for project 1 we have been probably worked with, and there were some issues. Some people looked at that their performance code, they were not happy because the thing is this: you can always run everything instantaneously if it doesn't have to produce a correct answer. Okay, you can just return. And so part of performance is also it has to have some correctness. Okay, so certain amount of correctness has to be passed before we can give a performance grade. So some people have this question, okay, mine, why I'm giving me a correctness grade? Because it seemed to run, but if you haven't done the right checks and stuff like that, then it's unfair for other people, because there's no way people who do the correct implementation can match that performance, because we are using that as upper bound. So make sure you do that. And another issue people had was, when you go to masters, you are going to work with 2 or 3 other students, or 1 or 2 other students. And in your group, you are going to share all the material with your group member and nobody else. But between the beta and final, you get an opportunity to basically get input from your masters and also see what the other people who are coming to your project in your discussion have done. So it's okay for you to see those code. You can't take the code home. You can't just say, give me a printout, I'm going to take home and re-implement. That doesn't count. But if you see some clever things they have done, it's okay to learn. Class is all mostly about learning. However, we have to grade you, so it's not all about grading, it's about learning. So we are trying to get a balance where we give the opportunity for you to learn from your peers also. So if you go look at other people's code, if you find something cool they have done, learn. And also, it's probably great for you guys to also tell other person, look, I did something cool. It's a good learning experience in there. So that's one opportunity you have to talk to other people in your group, on other groups, to basically learn something or find some interesting tidbits of how to get good performance. And hopefully, you will learn some interesting things and able to implement that to your final. Okay? So today, we are going to talk about memory systems and performance engineering. So if you look at basic idea about memory systems, you want to build a computer that seems to have a really fast memory. You don't want things to be slow. For example, long time ago, people built these computers where memory is always slow. Everything is fast, further away. It doesn't help anybody. The way we know how to do that is to build small amount of memory very close to the processor. You can't build a huge amount of things all close to you. That doesn't work. It doesn't scale like that. And then you made a caches like that, and you build larger and larger memory going down. And the illusion is you want to give the illusion of you have huge amount of memory. Everybody is very close to you. Okay, so it looks like you have millions of friends that you talk to everybody, and that doesn't happen. But how do you give that illusion? And the way that you give illusion is when you use normal programming practices, when you normally using data, people have found there are 2 properties, what we call locality. That means First thing is called temporal locality. That means if I use some data item, there's a good chance I use that data item again very soon. Whereas something I haven't used for a long time, I'm probably has a good chance I will not use it for a very, very long time. So can I take advantage of temporal locality? So that means some data will get reused a lot of time in a very quick succession. So those things should be very near to you because you might. Other one is spatial locality. That means if I use some data item, there's a good chance you'll be using data items next to that, closer to that. So can we take advantage of that? So those two properties help the compiler to fool the system, fool everybody thinking that it has this huge amount of memory very close to you. But internally it doesn't. Unfortunately, since it's trying to fool you, it doesn't work all the time. And when it doesn't work, it's good to recognize and be able to fix those things. So I showed this picture some time ago too. Memory is in a big hierarchy. L1, L2, in fact, we have L3 cache and a memory, disk, tapes, it can go up and down. And the key thing is when you go here, starting from registers, you have very small amount of things, very fast access. Here we have almost infinite amount of things, very slow access. And the two reasons why this has to be small, because first of all, those things are very expensive. And second, of course, you can't pack too much. And when you go down, things get somewhat cheaper. So that's also another kind of economic incentive here. So I talk about cache issues. And I'm going to go through this again because we are really going to dig deep into these things. So when you have a cache, that means you have a small memory close to you that's basically shadowing something sitting behind you. So when you ask for the data in the cache, there are many reasons why it's not there. First thing is cold miss. What that means is you're asking for something that you have never asked before. It's the first time you're asking. So the data is probably sitting way behind in your memory, where it still might be already in a disk. We haven't even loaded it in there. And the first time, you have to get it. So that get pulled in. And so this seems to be a place where there's nothing you can do. But another part of locality is a thing called prefetching. These modern processors have a crystal ball. They most of the things like branch prediction and stuff try to predict what you want to do. You can do the same thing in memory. You can look at what you have done, and Intel has this huge amount of circuitry that they don't tell anybody what they do, but they are trying to predict what you might fetch next, what data you might look for next. And if it is working well, something you had never ever looked before, it might deduce that you might need it and go get it for you. So if that works, great. So then there's a thing called a capacity miss. What that means is, as I said, I am trying to keep my best friends or the people I will be working with a lot. Oops, oh nice. What's going on here? Restart later, okay. So the people I'm going to work a lot with, close to me. The problem is I can have only a certain number of friends, and if you have more than that, I can't keep everybody. So hopefully your program is going to use a lot what we call the working set that can fit in the cache. And at that point, you get all those people into, it's like get everybody into one room, and the problem is if your part spills over from the room, then there's be a lot of issues. But if everybody fits in a room, things are very nice. You can have a good interaction, continuous interaction with them. And what happens is, if not, the worst case is the caches have eviction policy. Normally, it's called least recently used. That means if I don't have room in the cache, I figure out the cache line that I haven't touched for the longest time. I get rid of that, bring the next one. So that's a very good policy. It fits in your locality thing. But when will it not work? Anybody figure out when, if least recently used will create a really bad problem in capacity?
I mean, if you say that your working set is just one, like say you're like iterating through some set, and that set is bigger, like by one bigger than the
exactly.
Set, and you're
so
always missing.
Very good. So what you're going through, you're going around some data again and again. Okay? And that amount of data is 1 bigger than your cache line. You are going to have no locality because you're going to touch that, and when you go to, just before you use that data, they said, I need to bring one more data. I need to evict something. And who am I going to evict? The guy I'm going to use next, because it was the last thing, the least recent used thing. So it goes, and then you go there, and you have to bring that. Who's going to evict? You're not going to evict the one I just brought. You're going to evict the next one that I'm just about to use, and bring that one. And you go use that, and then to use the next one, you are going to evict the one you're just about to use. That. So by doing that, you basically get no locality. So that's a really bad problem in here. So another thing, interesting thing is called a conflict misses. Conflict misses says if you normally when you have a cache, so what you have is you have this large storage, which is the memory. You are going to map into a small storage in here, which is cache. So one way to say is any of these values, line can be anywhere here. That's called fully associative cache. Okay? In implementing that is somewhat complicated. So what the other extreme is called direct map cache. What that means is this segment, the same size here, can map into here. And then the next segment also can map into here. That means if you get this cache line here, it can be only mapped into one place in this here. Okay, this cache line can only be here, and also this cache line can also only be here if it is the same offset. So that means for every cache line, there's only one location in the cache. So here, what would be a really sad scenario? Yeah, I mean, I assume I have a lot of these slots. I read something here, and then next time I read something here, next time I read something here, and I go round and round this way. I might be touching only very few number of data items. But they're all mapping into one cache line, even though my working set is very small than the cache. I still don't have any cache usage because I'm having conflicts. And then there are two other misses when you're going to multi-process. We'll go to them in later lectures. One is called true sharing. That means there are caches private to each core. And what happens is if one core uses some data, you have to get the cache line there to use that data. If the other core wants to use that data, you have to bring the cache line back there. And the cache lines can ping pong between that. False sharing is even a worse way. So what happens is if the first processor here touches this value of the cache line, second processor touches this value of the cache line. We are not sharing anything. But unfortunately, two things I'm using sits next to each other. So when I write this thing, I get the cache line, he doesn't. When he tries to write this thing, he has to get the cache line. So I am seemingly using independent data, but I am bouncing cache line in between, and if that happens, that's going to have a huge, big performance impact. So these are the things. The last two we'll get to it a little bit later. So today, I am going to start with modeling how caches work with a very simplistic cache. So here's assume my cache. I have 32 kilobytes in here. This is a direct map cache. That means in my memory, 32 kilobyte chunks get mapped to this directly. Like this 32 kilobyte get mapped here. The other 32 kilobyte get mapped here. And the cache line side is 64 bytes. 64. And that means I have basically 512 lines here. 512 lines, 32 kilobyte in here, okay? So just remember this as we go on doing this, we will use this as a formula, okay? And you assume if you get in the cache, it happens in single cycle. If you miss, 100 cycles. Okay, so nice numbers, I mean, to do that. And so the first thing is we have a reference like this. Okay, you go from I equals 0 to I less than a very large number, AI. Okay, I just go through accessing memory like one after another, after another, after another, after. Okay, I have so you see how this is going on in here. So and also I'm accessing integers, so that means 4 bytes at a time in the cache line. So what happens here? So assume size of int is 4. So you're getting 4 bytes in here. So you're doing S reads to A. I'm accessing S elements in here. And you have 16 elements of A per cache line. Okay? You see why 16 is there? Because I have 64 in here, 64 bytes in here. Each time access is 4 bytes, so I have 16 of integers in cache line.
Bits or bytes?
Bytes. Bytes. Did I say bits? No, bytes. So what happens is if you access 16 element, 15 of every 16 is in the cache. Because when we are going one after the first guy, cache miss, I have to go bring it. And the next 15 I have bought through it. It's in the cache. So what should be my cost at the overall cost of memory access? I am accessing X data, and 1/16 of that is a cache miss. 15/16 is a cache hit. So basically, total access time is 15/16 of S is a cache hit, and other 1/16 I have 100 times cycles I need because it's a cache miss. Everybody got so far? Okay. So what type of locality do we have here? First of all, do we have locality? Who thinks we have locality? Okay, a lot of people think we have locality. What type? Spatial locality. Because what we are doing is we are accessing the nearby elements, even though we are not getting back to any of the data again. So we get some spatial locality access here. That's good. So this is our very simple, most simple thing we can do. So what kind of misses are we going to have in the cache? Cold misses, because I'm missing because I have never seen that data before. So it's a cold miss in here. Okay, so that's that. Let's look at this one. I'm accessing A0 S times. Okay, what's the total access time? How many cache misses am I going to get? 1. So I basically have 100 time for the first cache miss and S minus 1 for the rest. Basically, it's a hit. Okay, that's good. So what kind of locality is this? Spatial or temporal? There's not too many choices, or none. How many people think spatial? How many people think temporal? Okay, how many people think there's no locality? Okay, there's a lot of temporal locality. Okay, you want to get the covered. Okay, that's temporal locality here because you're accessing the same thing again and again and again, same data. So this is, oh, okay. You want to restart? Okay, wait a little. So this is the only time Windows is in a hurry. Every time I want to do something, I get hourglass. So what kind of misses are we getting? Trick question. I got 1 cold miss, and that's about it. And the rest I don't have any misses. So I have a miss, it's a cold miss. Okay, so here I'm doing something interesting. So what the heck is n is less, so I'm accessing AI modulo this 2 to the power number. 1 shifted to the n time is 2 to the power n. I shifted between 4 and 13. What is 13? Why is 13 less than 13? What's 2 to the power 13? I think I got this right. What's 2 to the power 13? Yeah, 8K. And I have 32K. So 8K of 32K cache. 8Ks of integers, which is each has 4 bytes, is how much? 32K. So what this says is everything I access should fit into the cache. I'm accessing data like that and going back and accessing data like that. I'm going back and accessing data like that. And it should all fit into the cache. Do you see what I do? I access up to 2 to the power 18 1. I go back and access that again. I'm just going back and back because of the modulo operation. Everybody see what's going on? So how many cache misses should I have? Assume there's, okay, how many cache lines I would be accessing if I am doing I mod 2 to the power n? I mod 2 to the power n. So one miss for each access line the first time round. Afterward, it's already in the cache. So how many access lines? 2 to the power n. Is that right? I think this is wrong. Oh yeah, this is right. Because every access, so in a cache line, how many? How many? This is 4. So there are 16 entries here. 16 entries in here. Okay. Only one of them basically misses that. So that means n. If there are 2 to the power n accesses. So you are doing 2 to the power n time accesses before you go back in here. So what you are doing is you make this many accesses before you go back again. Okay? And how many accesses are in the same cache line? You have 64 bytes in the cache. Okay, each access is 4. 16. 16. So that's 2 to the power 4. Yeah, but what I'm saying is, I might not access the 34 kbs because if n is small, I only access certain amount of cache line. So I'm accessing a part of the cache. I might not go through the cache. Everybody see this, how this is working? Because if I'm only accessing, we'll say, accessing 1, if this is, we'll say, 2 to the power 5. Okay, I am not going to access the entire cache line, entire cache, because I'm going to wrap around much before I go through the cache. So this many cache lines I'm accessing. Okay, and the first time I access that, I get a cache miss, and after that, everything is in the cache. Everybody's following me, or are we like lost in here? How many people are lost? Okay, let's do this. So what happens is, if we have a modular I mod 2 to the power, we'll say n. What that means is, I am going to keep accessing 1 to somewhere 2 to the power n, and the next one I am going to back here again. That's my access basically, because it wraps around. Okay, I'm accessing 2 to the power n. I nicely said n is between 4 and 13. So n is 13 means the maximum I can do is 32K. Not 32. Maximum I can do is 8K. 8K entries. 8K entries equals 8K entries equals 32K kilobytes of memory. Okay? So that means you don't have any option of overrunning the cache. Okay? So because the cache is a linear map, you don't wrap around in the cache. Do you see that? Okay, you don't wrap around the cache. So, but that means all these things is going to fit in the cache, and when you get around here, this is going to be in the cache. Because you haven't gone, the data you access is smaller than the entire cache. Okay? So what that means is only the first line has to have some cache misses. So how many cache misses you are going to have in the first line? Or any of the lines don't have cache misses because the first line still fit in the cache. We haven't evicted anything. We don't need to evict anything. How many cache misses have in here? The interesting thing is, so because these are 4 bytes, you have 32, we have 64-byte cache line, and you have each is 4 bytes. So that means I can do 16 accesses every time I have a cache miss. Okay? So up to here is 2 to the n. Okay, my cache misses, I do 2 to the n accesses basically. My cache misses is basically this much. Everything else is in the cache. And after first line, everything else is in the cache again. Because I nicely got my working set to fit in the cache, I'm really happy. Everybody see this? How many people don't see it now? Okay, good. So let's move to something a little bit more complicated. Aha, what kind of locality do we have? Good, you have temporal and spatial. Because you have spatial, because every time you go, you only get the first line of the cache, rest is in the cache. From that, I got a 16x improvement because I have temporal locality. And since I only access, when I go back to the data after accessing that, since it's already in the cache, I get temporal locality. I get spatial locality because of the 16 things are in the cache. I'm going through that. I get spatial locality. I get temporal locality because next time I access, it's still in the cache. I haven't evicted anything out of the cache. Okay, what kind of misses? Should be cold misses again. Cold misses, because the first time I get things, I haven't seen that data. After I get it, everything is in the cache. So now, here's an interesting case. Now I am doing 2 to the power n, where n is greater than 14. Now what happens? Now what happens in our picture here is I am going, so assume my cache is somewhere here. At this point, I fill up the cache. I still keep going. And minute I access something bigger than cache, what's going to happen? So I went through accessing 34 kilobyte. If I access the next one, what happens? Okay. No, shutting down, please. Okay. What happened? So I am accessing now more than I can fit into the cache. Next time I access, what's going to happen? Anyone take a wild guess?
The line before it?
New line replace something. New line replace line before that. New line in there. So what happens is then, am I ever going to have any temporal locality? No. Okay, so now first access to each line basically misses forever. Because by the time I get back to that, it's not there. It's basically it's gone out of the cache. So what that means is my total access time is basically every 16th element. I am getting cache miss forever. So what that means, every 15th or 16th I have a hit. So what I have is 15 out of 16, I have a cache hit. 1/16th of the time, I have a cache miss forever. So what kind of locality do I have now? I have special locality. I don't have any temporal locality. I don't never go back to something in the cache again. So what I have special locality. So what type of misses now? What do I have? Call, right. It's not shared. When you fill out the cache, you go back to get what's that? You fill the cache. So what type of miss is that? Capacity miss. Okay, so you have basically call and capacity misses happening now. Okay?
So the 100 that you multiply whenever you're trying to load from memory, is that like an arbitrary number, or is that actually the amount, like the actual cost of going?
Every machine, when you can get this beautiful table, I will go of what your machines have. We still have a number saying this is your miss rate, this is the thing. I mean, so some of these things you realize because of all the complexity, it's not that nice and simple, but this I just pulled out of the hat. And it's kind of normal, but. Aha, so what do I do now? I am doing the mod, but I am multiplying I by 16. So now I am accessing this value, this value, this value, this value in here. I am accessing this value, this value, this value, this value, this value. One value in each cache line. Okay? How much cache misses do you think I'm going to get? 100%. Every access is basically bringing a cache line. You're taking one value. I think if I go back to that value, I have already filled up the cache. So basically, I am first access each is in the cache. And what's your total access time? It will take a guess. Yep, 100 times x, because I have no. Okay, so this is okay. You don't have any locality. Okay, that was clear. What kind of misses am I getting now? Now I'm getting conflict miss. I get a call miss at the beginning, first time round, and then every time I do something, I'm getting conflict miss. Because the thing is now, this n, I am only accessing small amount of data. It doesn't fill in the cache, but I am not still getting any kind of sharing. So I'm having conflict misses. So in sake of time, I guess I will probably jump over that. So I just did, okay, if I do random access, what happens? So let me jump over that. You can do a calculation and figure out how many, probabilistically, how much you might have and stuff like that. Okay. So now if you look at what's going on, when you have no locality, okay, you don't have no locality. That's a pretty obvious statement. And then if you have spatial locality and no temporal locality, we think we are streaming data. That means you are going through data, but you're not getting back to it fast enough. So I have temporal locality. So I stream through data. So that means I go through data in a streaming fashion. Okay? And so what we have is if working shift fits in cache, you have in cache mode. If working shift is too big for cache, you can get some streaming mode and still get some locality, because we are bringing the lines in here. And you can do other things like optimization like prefetching we'll get to, and other issues. I don't address this last one, but to deal with cache accesses. So if we have more than one access, so here what I have is two nice arrays. Okay, each is a 2 to the power size array, 2 to the 19 power arrays. Okay, so now what happens when I put this into cache? Okay, look what happens in here. So what happens is this array get mapped in this one. This array maps this nicely in here. So what happens is this line can only be in this cache line, and this line also only can be in this line, the cache. Do you see what's going on now? So if you do this one, basically every time you access something, see, assume I'm accessing this data item. So I'm doing A, B. I access A, I get this line. I access B, what happens? So this line is gone, A is gone. Now I am accessing the next one in that cache line in A.
How do you know what cache line or how it will map to cache.
So normally in language like C, if we put two arrays next to each other, they should be mapped next to each other in memory. And if you want to be more adventurous, you can go to the assembly and see what the allocation says. So if you put A next to each other, you normally kind of get it next to each other. So what this one is, this is pretty bad. I should have gotten at least some spatial locality. I'm getting nothing. Do you see what's going on here? Do you know what's going on here? Now why I am not getting any spatial locality? Because I am bouncing. When I access this one is gone, even though I have more data in the same cache line. So I'm kind of bouncing two cache lines because of that. What's a good solution for this? Back there.
How do you hold that A and B will be mapped to the same cache line?
Right.
Because the thing is, A is a nice 2 to the power. A size is a multiple of the cache size. The size of A is a multiple of the cache size. So what happens is, if you have memory in here, you map something like A, see in here. If this is a multiple of cache size, so this is, assume this is 32K times some number, and you map B here. And then this is normally what happens in C, you put all the adjacent map allocations next to each other in memory. So you got A here, and you start having B in here, next to it. Okay, so what happens is now so if A starts, assume address, we'll say 100 just for this. This is 100 plus 32K times n basically. And they are all, when you do modular, this mod 32K, this same number. It maps into the same line. Okay, so what's the, I kind of gave you the problem. What can be the solution?
Now, allocate one line.
Yes, it's called padding. So one thing you can do is, okay, so I have no locality in here. Let me go to the next slide. What kind of misses? I have call and conflict misses. What I can do is just basically add a little bit of padding. I did 16 here. Normally you do is a prime number, so it will never clash with anything. Add a little bit of padding at the end of array. And that means the next array will not be conflicting most of the time. So a lot of times when you declare things next to each other, it's always good to add a little bit of a padding in between. Normally a small prime number would be a good thing to add as padding. So this one basically, now I start getting back my nice locality, because the two things are mapping to two cache lines. So now I get, what type of locality do I get here? Anybody want to take any guess what type of locality I have here?
So you define as you added the padding, you actually added just the extra 16.
Yeah.
Why would that just make the A and B interleave in the cache? I don't get
Because what happens is normally, it doesn't make A and B interleave in the cache, but it makes A0 not exactly match into B0. Okay, A0 will interleave with something like B16 or something. These things might map into the same place.
I mean, but are you reading A of I and B of I? Are you reading
Yes. Normally in a computation, people do that. AI equals BI plus something.
Oh, okay. So you're, I mean, so then that code is, like, I understand what you're saying, but I
Yes.
don't understand how that code actually fixes it, because they're both accessing I at the same time. So why would they be different, like, interleaving?
Yeah, because what happens is, so here's the problem. Okay, assume I have each is 32K. So I'm assuming a word length. Okay, so as first one is, we'll say you start with 100 plus I. Okay, and the other one is 100 plus 32K plus I. Okay, then you take a mod 32K, mod 32K, and this end up being 100 plus I This ends up with 100 plus I. So this is basically, if I is 1, it's a 101 element in the cache it's all going to map into. You see that? But now if I add 16 more to this one, then this map into 116 plus I.
I understand that, but I don't see that reflected in the code. You just defined it as for code. So how is B different from A in your code?
Because look at this, my S. I added 16 to S, so my A is a little bit bigger now. A is like, yeah, B is also bigger here. I don't care, B goes down here. B, I add a little bit more to the B, and it doesn't matter. I padded B too. So what that means is the first AI and BI are not in the same cache line.
How do we allocate A and B right next to each other?
So normally in C, if you declare something like int A, we'll say 100, int B 100, more or less they will be allocated next to each other. If you look at the assembly listing, it will say it got allocated next to each other in memory. Even in the stack, if you do that, if you allocate things, compiler has no incentive to go and move things around.
So this is only for global and local variables.
Global variables, local variables.
Does it still apply if you use malloc or new?
No, malloc basically will. The thing about malloc is, it might do something random, but on the other hand, it might, if it is fitting in the same page, it might also do something like that too. So it depends on how you do that. At the beginning, if you keep mallocing things, they might be contiguous. They might be a little bit off because malloc puts some metadata with each data. So it's not, if you ask for malloc 100, you're not getting exactly 100, you're getting a little bit of a bigger size, but you might have some contiguity too. But after some time, when you have done a lot of frees, we have no idea where it's going to go. It's random. Any more question? Okay, good. That was a good question. Okay. So what kind of locality do I have here? Now they are in two lines. I'm accessing each, and I got 16 times 15 out of 16 hits. What's that? Spatial locality. Okay. And of course, if you get spatial locality, you get called misses basically. And I think I forgot, you get what other type of misses? Before the conflict. Here basically capacitance, exactly. So in order to avoid this, what we have done is we make cache, instead of mapping into one place, beforehand what we said was we have this memory. And it's assume we have 32 sets, and if you have a cache like this, we make this entire map into this one, and this map into this one. What people have done is, instead of doing that, what you can make is make the cache, instead of one big block, two small blocks. So what that means is, this can map into this one, this maps into, my drawings are not that great, but I hope you get the picture. This map into this one. So what that means is each reference here, so maps here, and these two are basically conflicts. But now if the associated with 2, I can put this one here or here. I have two places to put the value basically. And that's called a two-way associative cache. Okay? So that means if I access something conflicting, if a two-way associative cache, you can access two things, still there are places in the cache for them to go. And there, one way to do, people say, is fully associative cache. Yeah, it can go anywhere, but that's very hard to do in hardware. So, but you can do some small number of ways. So in here, if you do two basic associative cache, in the first access in here, even though these are conflicting, these can go to one set and the other one can go to the other set. Okay, so two associative cache works, and so total access time, again I have nice locality in here, spatial locality, and I have both cold and I guess capacity misses. But if you have 2 associative cache, what's the next problem? How about if you have 3 different things? Okay, so if you have 3 different things like that, okay, now that I only have 2 associativity, it doesn't work because in LRU I will replace the last thing, and you might end up with nothing in here because you are replacing last thing, and the next thing replace the other thing, and basically after you get A, B, C, when you go to A is not there. When you go to B is not there. C is not there. You kind of go back to the same problem in here, and then you basically have to access everything again. And here again you have a special. There are some special locality, but cache can't use it. Basically, you have conflict misses. Okay, so you see that. So associativity is good because normally people assume you don't need that much associativity, but it's limited. So if you have too many things, you might run into this problem again.
So with position caches, do you have like less room in the cache before you get like what's called like crowding?
You mean capacity?
Yeah, before you get capacity.
Less.
Can you like put fewer elements in the cache before you hit capacity? Because it looks as though the matrix is just showing is using like half the cache by itself.
Because of associativity, you mean? You have multiple things? I mean, the thing is, since it's associated, no, because you have enough room. I mean, if you're going through linear everything, you have 2 places to put the name because it maps. So what happens is, that's a good question. So what happens is now, assume these many things fit into the cache before. Now, cache has 2 banks, and in each bank only this many things fit in, but the next thing can go to the other bank. So if you go through linear, you have the same behavior, even if you have associativity. So you can go and, because if the cache is the same size, the size is what matters for if you're going through linear access.
So for, let's say, the machines that we're working on, like, do they have a fixed kind of cache, or can we decide, like, do they have
a fixed kind of cache? It's built into hardware. And if you get I will show the table to say what type of associativity is in there. So is there
no way of, like, say, you have like 2-way associative or like 3-way associative, can you model, like, can you have like something on top of it so that it looks like if it's 2-way associative or something?
I mean, you can do things like that in software, but they're very expensive. I mean, think about cache is trying to fool a cache in that direction cannot be that easy because they are like really hard baked into hardware. That's a good question. But there are things you can do, not exactly modeling something, but kind of putting offsets and stuff like that so it doesn't get into these kind of conflicts. So yeah, I will answer this thing. Why don't you have more? Because if you go back to your 004 lectures, perhaps it might have explanation. It's hardware-wise, it's much harder to build. And if you have linked list now, so assume I have a linked list we are going through in here. And what's my reuse? Basically depend on allocation and use in some sense. So best case is everything is in cache. So I have a small list. And I go through again and again, round and round my list. Everything is in cache. And then as the sign is S, that's really great. Next best is everything is adjacent. Okay, everything might not be in the cache, but everything at least in adjacent memory. So I basically, first time I allocate, my malloc did a nice thing for me. And at that time, I basically get a nice, basically spatial locality. Since my size is 16 in here, so I get this much. And the worst case is random. Malloc puts it all over the place. Question?
If something goes into the cache, does the thing behind it and the thing in front of it also go into, do those both have like spatial locality?
What happens is normally cache is at 2 to the, we assume 64 element cache. So it's at that boundary. So basically 2 to the 8 boundaries is what happens. So what happens is cache line begins at 0th address, 64 address here. So if you get 63, okay, that means this value is not in the cache. So you get this cache line. So the cache line doesn't shift. It's fixed chunks in here. So if you get address 0, you get this one and all these things. If you get somewhere in the middle, you will get left and right both. But if you get here, you only get the right. So this basically, it's 0 and 64, they are boundaries in something. If you like 65, that's it. But that said, if you're accessing linearly, there's this thing called prefetcher. They say, aha, you're going through a linear pattern, and you might need that next, and it will bring this one for you. And what you find, I will show later, that in fact, the machine you are using has a really powerful prefetcher. So it can hide a lot of these things. So we'll get to that. So this is my total access time in here. Random case. Random case is basically every time I access something, it's not in the cache. So okay, I just put okay. And then if you have a bigger struct in here, but assume I have this big struct in here, but I am only accessing one element of the struct in here. I do that a lot. I created this large struct, and I am iterating over all the things in the struct, and just basically looking at my data. Only one element. What's the problem here? So I have this, okay.
So you're essentially skipping cache lines.
Exactly, so I bring the entire cache line, but I'm only using a little bit of it. Because I bring all these things into the cache, it comes with accessing that, but I'm only using data. So basically what happens is, if everything in the cache, I have access time S, that's great, that's not a problem. But if I do streaming, I only get, even though I'm getting spatial locality, I only get half of it. Because even though I'm bringing the cache line, only 2 of data, because this is 32 bytes long, is in my cache. Even though I'm bringing all this data, only 2 of them are in the cache, because rest of this other data is kind of hanging in there with me. And so I don't get that, and random, of course, you have no locality. So how can I basically make this better? How can I make this better? Okay, I just showed it very fast. I guess I was, okay. Aha! So instead of, if I assume I have this large data structure, but most of the time I am only accessing a small part of it, okay? This is kind of a little bit of a hack. I mean, this is kind of going against, I guess, 6005 type kind of building, but this actually will work. What you can do is you can go back, and instead of doing structs, what you can do is you can do arrays of each data item, okay? And now what happens is I am basically bringing this, and then the data I am accessing is basically right now next to each other. Because if I am accessing only C, so you might have this very large data structure representing something. You have a lot of them, but most of the time you're only using few of them. So you don't have to be structs of arrays. You might have to have a couple of different data structures. One is the one that you access regularly, put them, hopefully get them next to each other. And the nice thing about arrays is it guarantees things are next to each other. Of course, managing it is harder.
The arrays are separate from the struct. You use the struct when you need the struct. And
You can't do both. So that means you are, instead of doing the structs, you use arrays of each field. So instead of that, so instead of doing this one, you just do this one.
And basically, instead of being able to pass the whole, so say, like, now you have to kind of be able to know and manage for yourself what data is where, because you cannot just pass the struct to like a function.
No, you can't pass the struct. You basically have to pass the index in here for this structure, basically. So you have to know something in there. So this is lot messier, but it can actually give you a performance if you do this type of access. So it's not something you won't do everywhere. That's why you still want to use structures and nice classes and stuff. But this, if you're doing very large data, but most of the time you're accessing only small amount, this kind of representation can help. Aha. So I want to get a little bit into matrix multiply. So what we are looking at is this 4x4 matrix. And you can represent it using this representation. But to make it clear, what I'm going to do is I'm just going to allocate this entire thing as a single array. And I'm going to do the address calculation myself. Okay? Because if you go a little bit down, you realize this is allocated in a little bit of a weird way. Okay? And so this is what we call row major order, because all rows are next to each other. And you can access allocated column major order by just basically, that means now A0, 0, 1, instead of that, 1, 0 is next to 0, 1, 0, 0, 1, 0, 2, 0. And then basically saying same thing, one, instead of saying 4i plus j, I just 4j plus I. Okay, you can do both. So this is my nice matrix multiply function, because if reason I did it this way is very clear how my accesses are going to use. So if you look at C, let's look at only the inner loop. Most of the mapping matters in the inner loop. I go for k in 0 to size. Only first access of C is going to miss, okay, because it's going update in same k, da 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 da. So C is very nice in here. You only get one missing here. You have a question? Okay. A has a streaming pattern, because every time I update k, I go to the next element, next element, next element, next element of A. What type of a pattern do I have in B? I have, yeah, exactly, I'm jumping on memory. I'm jumping one to another. So if you look at that, I am going through A like that, and B, and going through C one element at a time, basically here. So if you look at doing this, in order to calculate one element of A, in here calculating this, what you have to do is I am getting B and C this way. I am going through a row here and column, and this row nicely will fit into the cache line through that, because this is the memory. But C is just jumping all over the memory, and I am having no locality in here. So what can we do here? What's the simplest thing in here? How do you get some locality into the C? Aha. So yeah, you are getting a, that's the next thing. What's more simple thing? That's a more advanced thing you can do. We'll get there. What's a simple thing you can do for C? Transpose. So what we do is, so here's the overall execution time original. And voila, when you transpose that, you can actually get a huge benefit in here. Because now I get a special locality in both sides in here, okay? And so now when you're transpose, I'm going through like this. So now what I did was I am giving this CPI, and what happens is when you transpose, I have like a 5x improvement in CPI. That means instructions are actually not waiting, not doing nothing. I have a pretty good increase in cache miss rate, or reduce of cache miss rate, because now I am actually going through cache very nicely here. So the next thing we can do is what she just pointed out, blocking. So instead of matrix multiply, just multiplying just matrix at a time, you can multiply submatrices and calculate small submatrices. And if you do that, the submatrix can nicely fit in the memory. So let me show you that. This is the blocking code. Okay, let me show you what that means. So what they are doing is you are calculating, you are multiplying this matrix by this matrix in there and getting this matrix. So what that means is normally what you do is to get one element, you have to multiply a row and a column. Normally, we are calculating a row of A at a time. In order to get a row of A, I have to get a row of B, as entire C has to participate in to calculate A. So by the time I have calculated 1024 elements, I have gone through this many accesses to new elements, basically. Because I am getting B again and again, but I have to go through the entire C in here. So this, if this much data is bigger than the cache, I have no locality in here. Okay? But if instead of calculating a row, if I calculate a 32 by 32 block, which is again 1024 elements I'm calculating. If I do that, I need a block here and a block here, and I only touch this much data. Okay, that's I'm getting the same amount of output, but because of reuse, I get touched lot less input in here. And just by doing this transformation, I can really reduce the amount of data. I can create a smaller working set, go through that much more, and reduce the amount of cache misses you get. So by doing that, I basically got another 3x improvement in my CPI, really brought down my L1 cache misses, and basically eliminated L2 cache misses. Okay, so I got a really good speed up in here. So you can block multiple levels, L1, L2, L3, because every time you figure out the working set size, you block, so the data in that will be set in the cache in here. And this is kind of nasty to do by hand. We'll see. Okay. So the other interesting thing is call stack locality. So if you do something like fib in here, traditional fib, if when you do fib4, you calculate fib4, fib3, fib2, you kind of build the stack, go up, back again in here. So if you keep doing that, the nice thing is you're going up, but it's, okay, hopefully one of these days I'm going to hit the wrong button. And so what has is we have, what kind of locality do we have if we are doing accessing data like this in my call stack? Oops. What kind of locality do I have? I mean, I access here fib4, and I get back to fib4 here. So within each frame, I am accessing data next to each other. So I have a little bit of a spatial locality, because in each frame, all the data is next to each other. But across frames, normally I will have some temporal locality, because I'll get back to that data sometime. Okay? So to kind of summarize here, what you want to do is, if you have patterns like that, okay, before summarize this one, if you are reading lot of data, processing through stage 1 to stage and producing results, that means you're reading a huge amount of data, do stage 1, save, read it, the save data again, do stage 2. You have really bad cache locality. One thing you can do is read a small chunk, do all the stages on that small chunk, save it, and go to another chunk. So instead of doing the entire data, doing something entire data producing, you can do this chunkifying, and by doing that, you can get a lot of locality. So once you bring in data, you like to do as much things as possible to that data before it gets out of the cache. That's the entire thing about locality, and you can restructure code to do that. So if you look at that, what we have done today, we have looked at things like associativity, cache lines, cache sets in here, and how to address and map to a cache. We kind of did this thing. And we look at something like streamings versus in-cache versus no locality type patterns. And then when you look at data structure transformation, we look at how to basically replace structures with arrays and split data structures to make sure that you get a lot of good, nice locality if you access a certain amount of data. And pack data to get smaller cache footprints kind of things. And we also look at kind of computer transformations, things like transpose, copy in, compute, copy out type things you can do, so you can actually get nice data, nice locality. So you can do both data and compute transformations. And do things like reorder data accesses and recast computation stages. So this is kind of a summary. Next thing I want to go is look at what machines you guys are using. So this is the machines we used last year. Okay, these were quad cores, and it had L1 cache. So this is all the data used. So this has a 32 kilobyte L1 cache, data cache and instruction cache. There are two caches in here for data and instructions, each core. And then the cache line size is normally 64 bytes all triple. And here latency, if your data hits here, you get 3 cycles. Okay? If not, you get 14 cycles to go to L2 in here. Okay, if data doesn't meet in there. And associated, these were all 8-way, and this was a 24-way associative cache. So that was what we did last year. So this year, we have a bigger machine that has multiple levels of caches. So you have, each core has L1 instruction and data cache. It's kind of the same, 32 kilobyte cache, 4 nanosecond latency in here, 8-way and 4-way. They kind of reduced that. But they added 256 kilobyte L2 cache in here, and then a pretty large Himango 12 megabyte L3 cache in here. The interesting thing is here, there's pretty fast access to these ones. If you miss in here, this is about 2.5 times cost from going from here to here. From here to here is about a 5 times cost. So here to here, so 5 times cost. The interesting thing that actually surprises a lot of us was here to here cost is not that different. 50 nanosecond and 75 nanoseconds. So actually memory, even though it's sitting out in there, they have managed to get it pretty cheap access here. Normally, my intuition says this should be much higher because you're going off chip. So this is the structure here. It's a lot more complicated. So here's something I produced last year. So what I did was I ran this program. Okay, and in these machines, there's a way to turn off the prefetcher, the previous generation. So when you turn off the prefetcher, when you run, what you are doing is I am accessing data with a working set, small working set, little bit bigger working set. So this is basically what you consider working set size. So you get a graph like this. So this is, I am hitting my L1 cache. Okay, and if it is more than that, I start smitting on L1 cache, I go to my L2 cache. Okay, and if L2 misses, I have to go to main memory. Okay, very traditional kind of a graphing here. In fact, I did some another little bit of interesting thing, which is instead of accessing next item, I kind of skipped in here. So this is trying to force basically how to do get conflict misses. And so if you line up things like this exactly, what happens is you get these conflict misses, and you get this number. So I have interesting story to tell. Like when I was a graduate student, we were running this bunch of benchmarks. And normally when you run a benchmark, you try it for n equals 64, 120, 256, 512, and stuff like that. And we got this graph like this. I mean, we have expected graph going like this in here. Okay, you're like, okay, that's our benchmark result in there. Then at one point, by accident, instead of typing n equals 64 or something, I typed n equals 63. And suddenly I got a performance like this. Wait a minute. What's going on? So in here, what I got was not a line. I got like 16, 32, 64, 128, nice graph like that. And then I just did 63, like get here. I'm like, geez, that can't be right. And then I started looking 62, it's here. 61 here, it's here. So I realized if I enumerate all those things, I got a graph like this, basically. Kind of something like this. And the thing is, if I have never tried this 63, I would have basically thought my performance is like this. So far worse. Never realized, because it was all having conflicts in memory, because I am doing nice 2 to the power numbers. So this is what happens. So if you just look at 2 to the power numbers, you will think, yeah, this is the performance you're getting, without realizing that, in fact, you can get this far. So this is great. So I ran it on the new machine. The problem with our new machine is there's no way to turn off prefetching. Okay, so this is what you are getting. Everything, because I'm accessing this nice linear, looks same. This is exactly what you want to happen. What it's doing is, minute you go to the access, it realizes, aha, you are accessing linearly. It starts fetching data in front of you. It's going to catch up. It starts feeding your data. So you're not going to have any cache misses, because you are going through this nice linear pattern, and you just basically end up with this basically beautiful graph, which is gives the feeling your working set could be now gigabytes long. I mean, this is basically at this point I am fitting into the entire L3 cache, and still look like this works beautifully, because this is what you want for it to figure out. So now I'm like, geez, this is great. This means my cache works. It's very nice, but I want to show you guys what's going on. So that doesn't help. So I came up with this program. So this program, what I did was, I created a working set, but I am accessing randomly within that working set. I created this address. This is my poor man's random number generator. So basically, I am adding basically number in here and multiplying this, and then masking this to get the right bits, basically. So I get within that set in here. And then I just access data. So I'm getting access random. So I get a number like this, and just jump up here, and then I have this kind of behavior. So okay, so now I need to, this is a lot more complicated. I need to figure out what the hell is going on here. So I said, okay, let's now look at performance counters. I look at L1 cache miss, okay, up to 32K. I have no cache misses. Boom, cache misses jump up. Perfect. And I have this little bit of a kink in here. This beautifully describes, because I have a 32K L1 cache, and until then I have no things, and when mini cache start missing, I'm jumping up. Perfect. I got that description here. Then I look at my L2 cache misses. This is, I think the L2 cache in this machine might have a little bit more complexity than Intel is telling us, because this is not going like here and jumping up. It has a 256K L2 cache, I guess. This is 256? Yeah, can't remember. 250 is, okay, remember these things, okay? So we have 32, 256, 12 megabytes in here, okay? Even though if you have 256 in here,
Should be 256 or 32?
because everything is backed up, it's hierarchical, so it's not additive, it's not next to each other. So all those, because at this point L1 is useless, L1, everything is just going to L2. So L2 is the one who's serving it, okay. Come on. Okay, so happening here, so what happens is in here, it's normally should start jumping here, 256, but start jumping earlier, so there might be some other interesting thing going on in here. It might be interesting to investigate. So this is okay. So still I'm pretty close. I realize this jump is basically because of L2 happened, this jump in here. L2 start missing. Then I look at L3. It's here. Now what's happening here? So this was a big mystery between two of us were like trying to debug about 1 hour ago. So not 1 hour, probably the class is gone for like 2 hours ago. We were trying to figure out, okay, wait a minute, this doesn't make sense. My performance is here. L3 is, it should be just basically nice flattening out here and just jumping. It's not doing that. And we're like, what's going on here? So then we were scratching our heads and we start looking and say, there might be other things going on. We looked at this thing called a TLB. Let me tell you what TLB is. What we realize is at this point we are still in TLB misses. Okay, how many people know what a TLB is? Okay, good. So let me spend last couple of minutes explaining what a TLB is, and that kind of explain what's going on in this graph. So TLB means normally the data is stored in memory on using real addresses. That means there's a memory size in here. There's an address from that. There's certain memory size. And then the programs want to use virtual memory. That means programs want to feel like they have a lot more memory than actual physical memory available. So what happens is you have virtual memory address, but somebody has to map virtual memory to physical memory. So the way it works is there's a thing called translation look-aside buffer, TLB, that says if you give this virtual address, here's the right physical address. So of course, you can't do it for each address by address. What you have is you have 4K pages. So the address space is broken down into 4K pages. Each page will have an entry in this TLB saying if you get this virtual address, here's the right physical address. Okay? So normally what happens is when the operating system, they create this large table for every place in memory, it gives this table and it loads into memory. Then the hardware will fetch and cache some of those entries in this TLB cache in there. So normally what happens is in here, it caches 512 entries. It can keep 512 entries to 512 pages saying here's the mapping. The problem with 512 pages is in a 4K byte page size, 512 pages can only hold 2 megabytes of data. Okay, if you're accessing more than 2 megabytes of data, you have to go more than 512 pages, and at that point, that mapping is not in the TLB. And that means that you have to go do a mapping translation. The problem for this is this 4K pages is a very ancient artifact. There's new machines, you can ask for what we call large pages or super pages. You can ask for 2 megabyte or 4 megabyte pages. If you ask for super pages, then of course 512 entry is good enough. It can hold enough things to basically not to have TLB miss, at least while you're in the cache. But since Linux, without doing anything, only asks for 4K pages, before you run out of your L3 cache, you run out of this TLB table. And it has to start fetching and fix the table. That means you have to actually fetch the table entries, and so you have to do more fetching. So that is why this is even running higher, because it's trying to fetch these TLB entries and stuff like that. Question?
Is there a way so then to actually fill with the TLB so that it actually, so that you actually fetch bigger pages?
So in allocation, you can ask for super pages or large pages, but in Linux, normally it just asks for 4K pages. So the operating systems haven't kind of caught up to the current hardware. And this was built, assuming, because it doesn't make sense, TLB to run out before you run out the cache. I mean, that's kind of mismatch in here. But it's built assuming you will get large pages, but if you don't, you're going to run out of the TLB in there. So this is why sometimes performance engineering is interesting, exciting, and frustrating. Because you assume you know what the hell this is going. You assume this is going to go here and that, and suddenly this NIC shows up. And so we had to stretch our heads, and luckily, we found what's going on. But we could have spent hours or days trying to figure out what's going on here. Because there's one insight, this clear inside TLB, which says, OK, let's try TLB, and it worked. That was really good. But I could have I have many cases, spent days trying to figure out what something is going on. Because performance is kind of an additive of everything. There's no nice abstractions and stuff like that. If you think abstraction-wise, somewhere outside the abstraction that's going to kill you. So that is why it can be interesting, because you have to know everything. And the fun thing is, once you understand performance, you basically understand end-to-end, soups to nuts, what's going on. OK, with that encouraging thought, let's see how you guys do in the next part of project 2.